In 1965, the Soviet Union faced a dilemma. The scale was unprecedented. The nuclear age had arrived. High-altitude bombers flew faster than ever. Old defense metrics became obsolete. The Soviet Air Defense Forces were called PVO Strany. They operated as an independent branch. Their mandate was singular and vast. They had to defend the largest landmass on Earth. They protected it from catastrophic aerial attacks. To understand 1965, look at geography. Also look at time itself. Soviet borders spanned wildly different terrain, from the desolate Arctic north to complex western and eastern borders. A hostile bomber crossing that perimeter left little time. Interception windows were incredibly narrow. Time became the most critical resource. Jet aviation crushed response times drastically. Hours shrank down to mere minutes. Isolated radar posts could not keep up. Localized decisions were mathematically insufficient. They could not protect industrial hubs. They could not protect command centers either. Massing interceptors alone proved useless. Anti-aircraft guns alone were not enough. Without coordination, none of it mattered. PVO Strany needed a rapid nervous system. It needed centralized coordination immediately. The strategic context demanded a paradigm shift. Human observation had to be replaced. A cohesive technological architecture was required. Analog defense could no longer work. Continental-scale protection was now essential. This urgency catalyzed automated command systems. These systems reshaped aerospace defense entirely. They laid groundwork for future networks. Modern integrated air defense followed directly. Before automation, Soviet defenses were bottlenecked. Human operators faced severe limitations. The manual system was slow and fragile. It relied on many manual steps. A frontline radar detected a contact. The operator watched a faint blip. He estimated heading and altitude manually. He reported it over an open line. Command centers used physical plotting boards. These were called planchets made of plexiglass. Plotters traced positions using grease pencils. This manual process introduced serious delays. Every second lost let bombers advance. The ODA loop moved painfully slowly. Observe, orient, decide, act all lagged badly. A commander studied the board manually. He extrapolated the target's future position. Then he issued verbal scramble orders. Interceptors launched under manual voice command. A GCI officer read delayed radar plots. He transmitted vectoring commands by radio. Turn left, heading 270. Climb to 10,000 meters. Voice communication was noisy and unreliable. It was vulnerable to jamming constantly. Misinterpretation and human error were common. Manual systems handled few tracks at once. A saturation attack overwhelmed everything instantly. Dozens of bombers created total chaos. Plotting boards became unreadable grease pencil messes. Command structures suffered catastrophic cognitive overload. This system suited an earlier war. Could not handle jet age speeds. Latency created a fatal defensive gap. Engineers needed machines to share data instantly. The answer to manual latency was Vozduk 1. It meant Air 1 in Russian. Deployed widely by 1965, it transformed everything. It was not a simple upgrade. It reinvented radar processing entirely. Engineers built it from electromechanical circuits. Early vacuum tube logic powered its core. Its purpose was automating interception completely. Its genius bypassed human plotters completely. No operator interpreted flickering screens manually anymore. A long-range radar like the P-14 detected targets. Raw returns fed straight into the network. Analog computers and vacuum tube logic took over. The system extracted coordinates, speed, and heading. This profile moved through the ASPD-1 link. Transmission was secure and nearly instant. The ASPD-1 acted like a military intranet. It connected radar sites to command centers. It also linked directly to airbases. Data no longer needed manual drawing. Automated consoles projected a synthesized picture. Commanders saw the airspace clearly and quickly. The true triumph was target calculation itself. Onboard computers ran complex intercept algorithms constantly. They compared bomber paths against interceptor performance. Aircraft like the Su-9 were factored in. The MiG-21 was included as well. Vozduk-1 calculated intercept geometry automatically. It determined the exact scramble moment. It set the optimal climb profile. It calculated the precise firing vector. Automation reached directly into the cockpit. The Lazur data link guided pilots directly. Steering commands appeared on flight instruments. The attitude indicator displayed live guidance. Pilots no longer waited on frantic voices. Command indicators guided the most efficient path. Corrections arrived instantly, without any radio delay. This mattered greatly at high altitude. Fuel burned fast at those speeds. There was zero room for navigational error whatsoever. The system guided interceptors toward the target. Onboard radar then acquired it directly. Only then did the terminal phase begin. Data fusion and automated vectoring compressed everything. Old latency from voice and pencils vanished. PVO Strany tracked many targets simultaneously. Interceptions happened at true supersonic speed. Scattered radar dishes became one machine. It responded with mathematical precision instantly. No fragment of the old network stayed isolated. This became the benchmark for future systems. Field operations formed overlapping, layered tiers. The outer tier held early warning radars. These sat along borders and coastlines. They concentrated near expected bomber corridors. The Arctic and Baltic were priorities. Massive antennas scanned constantly, day and night. Nothing crossing that outer line went unnoticed. These installations acted as sensory organs. They fed detection data into the system. Once a target crossed the frontier, regional Vozduk-1 nodes engaged instantly. They scrambled interceptor squadrons immediately. Hostiles were engaged far from targets. If interceptors failed, missiles took over immediately without hesitation. The inner tier held SAM belts. These rings encircled critical centers heavily. Moscow held the most dense defenses. Layered rings surrounded the capital repeatedly. The S-75 handled high-altitude targets. The S-125 handled low-altitude threats. Together they closed every possible gap. Automation allowed seamless handovers between forces. Fighters and missile batteries never overlapped. This prevented friendly fire completely. It also prevented wasted ammunition entirely. Managing this scale required massive infrastructure. Hardened communication lines were essential everywhere. Power generation fed the radar arrays. Backup generators guarded against sudden failures. Strict synchronization linked military districts together. Every district trained toward the same protocols. Regional centers acted as autonomous hubs. They managed sectors independently if isolated. Yet they shared telemetry when connected. Command could reroute forces across regions instantly. This turned Soviet airspace into one organism. Every node, radar, or missile worked together. From a lone dish in Siberia to batteries near Leningrad, each piece served the wider defensive whole. Despite its power, the 1965 system had limits. This hardware relied heavily on vacuum tubes. These components were massive and hot. They needed constant, intense cooling. Failures were frequent, requiring endless maintenance. Technicians replaced burned-out tubes almost daily. Processing power had a finite ceiling. The system handled moderate groups well. It struggled against massive saturation attacks. Hundreds of bombers exceeded its bandwidth. Coordinated jamming multiplied that same vulnerability further. Electronic countermeasures posed serious challenges too. Early data links were vulnerable to jamming. Western adversaries developed sophisticated countermeasures quickly. Their engineers studied Soviet frequencies relentlessly. Centralized control created a single point of failure. If a node was destroyed, guidance degraded severely. Entire sectors could lose coordination instantly. Pilots then reverted to manual methods again. Despite these clear limits, its overall achievements remained undeniable. Continental airspace could be managed by computers at true continental scale. This was proven definitively by 1965, for the very first time anywhere. Lessons from Vozduk 1 shaped future systems. They laid groundwork for digital air defense. Every later Soviet network built on its foundation. Modern integrated networks trace back directly here. It shifted defense from observation to algorithms. This changed aerospace combat permanently and completely. The concept endured far beyond its era. Its legacy lives in networked battlefields today.